Next topic is SAG. What is SAG? If you are erecting a transmission line, this is the mechanical design of a transmission line. If you are going to erect the transmission line, there we have to consider this SAG. That is an important thing which you have to consider when erecting the transmission line between two poles. Why? Because the amount of SAG which you are going to keep between the two is based on a calculation that we are going to see now. And that will be very simple if it is a level support. That means both the towers are at equal height. If the level is different, then the corresponding calculation is somewhat tedious and you have to find the corresponding line side. So here, the first diagram, if you see that there are A and B are the two supports. A and B are the two supports where present at equal distances. And so that if you see the shape of that, it is looking like a catenary shape. Okay. And the middle point is almost at the center of the circle. If the distance between the two span is 30 meters, the minimum point of the conductor is exactly at the middle, which is at 15 meters from either end. That is the first case. Then, here the definition of SAG is the distance between the highest point of the tower and the lowest point of the conductor is called as SAG. The difference in level between highest point of the tower and then to the lowest point of the conductor will give you the corresponding SAG. The S is called SAG. There are some places where, see the second case you can take, A and B are the two unequal level supports, so that both are looking like this, both the shape, it is almost parabolic in shape. And here there are two SAGs are possible. One is from the lowest tower to the lowest point, the SAG is called S1. From the highest tower to the lowest point, the SAG is called S2. And the difference between these S and S1 and S2 is called as H. H you can able to find. H is the difference in level between two SAG, then you can able to find it. And here in two unequal level of supports, we assume some of the variables like x1 is the distance from the lowest tower to the lowest point of the conductor, and x2 is the distance between lowest point of the conductor to the highest tower, and the total line length is L. These are the assumptions we made. Okay. Coming to the line side, while erecting a transmission line, an overhead line, this is also once again only possible or only way you have to calculate in an overhead line. It is not applicable for cables. While erecting an overhead line, it is very important that the conductors are under safe tension. Why we have to particularly calculate the SAG mean? Sometimes if you stretch the conductor to reduce the SAG or to reduce the amount of conductors which is required for a particular transmission line overall length, if you stretch the conductor between that, the length or the SAG will be less, but the tension will be more. SAG and tension are inversely proportional. SAG and tension are inversely proportional. So that what happens in the sense, SAG, lesser the SAG, more the tension. And if you allow more SAG, suppose if I want to keep it as more safer side, if I go for more SAG, I am not worried about the cost of the material. If you give more SAG over there, so that the tension will be less, and at the same instant of time, it will be the distance between the lowest point of the conductor to the ground level may be decreased. That also we have to take. There should be a minimum clearance between the lowest point of the conductor to the ground level. Yeah, these things you have to take. Yeah, this is the representation of tension. If you stress it, tangentially there is a force acting from the mid of the portion, that is called the tangential force, and those things we are going to calculate. So the simple definition of SAG is the difference in level between points of supports and the lowest point of the conductor is called SAG. Yeah, just SAG and tension calculations. This is for equal level of supports. When supports are at equal level, A and B are, as I said earlier, A and B are the equal supports, and the lowest point is O. We assume that there is a small portion P. P is operating point, where at that point there are two forces are acting. One act vertically, other one act horizontally. The vertical force is the weight. W into X is the vertical force which is acting at a distance of x by 2, and there is a tangential force which is acting tangentially, so at the distance of y from the operating point P. So with this, if you calculate that, the corresponding SAG is WL square by dt, where L is the total length of the span, T is the tension of the conductor. By considering all the forces, see if you see the expression, how we are getting the expression, since I am equating both the forces. the vertical downward force and the horizontal force at one instant of time both should be equal. That is why Ty is equal to Wx into x by 2. If you substitute there, then you can find x is equal to L by 2 over there. Then the corresponding value of SAG is WL square by 80. This is the formula. When supports are at unequal level, we have to calculate it. I said that there are two distances we assume, one is x1, other is x2. Our aim is to find x1 and x2, and the general formula, whether it is equal level or unequal level, the general formula is Wx square by 2t. If we substitute x is equal to L by 2, because in equal distances, the value of x means the distance between the support level to the lowest point of the conductor. In equal level, it is L by 2. That is why if you substitute L by 2 there, it is WL square by 80. That is the equal level. In unequal level supports, you have to find the value of x1 and x2 because both are different. In that case, if you find the value of x1 by x2, there are two conditions over here also. You find the SAG at different level, then h is equal to s2 minus s1, that is already known. You substitute there, there is another equation called x1 plus x2 is equal to L. Substitute there and find the value of x1. We have two expressions, one is for x1, other is x2. Using this, you can able to find the distances. When x1 is known, you substitute in the general formula Wx1 square by 2t, so that you can able to find it. So that is about the SAG. So to find the SAG, first you have to see that whether your supports are at equal or unequal level. Accordingly, you have to choose the category. Okay, that is a conventional way of doing the thing. But practically, if you go and implement a transmission line, the force which we consider for calculation is only the vertical force due to weight and the tension due to its own self-weight. But is it the case in the practical system? No, because due to the wind blowing, sometime it will get tilted, and that is called a slant sag. There are some cases where even in western countries or even in our northern part of our country, there are some ice coating over the transmission line, so that the total weight will increase. You see that the diameter of the conductor, you see the diagram, D is the diameter of the conductor, T is the thickness of the ice which is formed, so that the effective diameter is getting increased by D plus 2T. And the entire area is subjected to wind force. So if that is the case, once again your formula is getting modified slightly. See, this is the normal weight, W plus Wi is due to ice formation, and your wind force due to that also your horizontal force is different, so that the total weight is Wt. So Wt is W plus Wi whole square plus Ww whole square. You see this formula, you have to find the weight. Since there is a change in weight, once again go back to the formula. S is equal to Wx square by 2t. Your total weight is different, that is why everything is getting different. So that is called the slant sag, which is vertical sag by cos theta, that will give you. To find the tension, I always saying that there is a tension which is acting tangentially. How to find the tension? Which is the relation between working stress multiplied by conductor area. It is based on the size of the area. Otherwise, using the ultimate strength by safety factor, you can find the working stress, and the conductor area is given by the manufacturer itself. You can able to find. Yes, these are the various numericals based on SAG that we are going to see. Here. Next, what are the various types of conductors? Because if you go for a mechanical design, first thing you have to see about choosing of material. Okay, for choosing the material and what are the various types of conductors which is available, and what are the various parameters which you have to see while choosing the conductor material. When the conductors are used in a transmission line, nowadays most of the cases we have ACSR conductor only, aluminum cold steel reinforced conductors only we are using. So for this, they should have low weight, they should have high tensile and fatigue strength, they must have high conductivity, they should have low coefficient of expansion, low corona loss, they should have less resistance and low cost. These are the factors you have to see while choosing the material. Here. Then, the advantage of using aluminum. I said that the ACSR is a conductor. Why we go for aluminum? If you go for aluminum, cost wise it is less. Our ultimate aim is how to reduce the cost of the entire transmission line. In that case, majority of the cost is going for selecting the material of the conductor. If you replace this with a copper material, even though the conductivity is more, because of its cost, what will mean the overall cost of the transmission line is increased by 30 to 40%. So that is why we have to go for low cost. That's why low cost material is aluminum is one of the low cost material. Less resistance and corona loss, less weight. That is an advantage of aluminum. Advantage of aluminum is Not only the cost, the total weight of the aluminum is less, so that the amount of support which you need to support the entire transmission line cost is also reduced. So several conductors which are made up of aluminums are all aluminum conductors is said to be AAC. Triple AC is called all aluminum alloy conductor. ACSR, that is a conductor which is almost we are using aluminum conductor with steel reinforced. ACAR is the aluminum conductor with alloy reinforced. So these are the different type of conductors which you are using. Yes, you can see that ACSR. Why ACSR? In the sense, even though the weight of the aluminum is less, the weight of the aluminum is less, not inside the tensile strength. The tensile strength of the aluminum is poor. Due to that, what happens is if you pass some amount of current, due to heat, it will get elongated, and due to cold, it may be getting contrasted. So, to overcome these things or to improve the tensile strength, what we are doing is we have to go for imposing the steel inside the aluminum conductor. So, aluminum are the present outside, and you have to put the steel strands. These are all called the strands which are present inside, so that the overall conductor tensile strength is increased. Okay, so ACSR conductors are commonly used as they have following advantage due to high mechanical strength, and the SAG is small, so that is why we have to go for. They have low corona loss. Skin effect is less. We didn't know about the skin effect so far. What is skin effect in the sense? If you take a conductor, if you replace these conductors with a solid conductor, most of the time the tendency of the current is concentrated at the surface of the conductor only. Due to that, we are not replacing the effective area. That is one case. And also, most of the time, the outer strands is getting, or outer parts is getting punctured. So that is called skin effect. To overcome that, only we have to go for standard conductor. Even that standard conductor nowadays is replaced with hollow pipes also. That is to reduce the skin effect. All aluminum conductors, the conductors made from aluminum alloy are suitable in urban areas as they provide better tensile strength and conductivity. These alloys are known with different names in various countries. Some of these alloys are costly as they are heat treated. Okay, aluminum conductor with alloy reinforcements. This is also a type of aluminum product, but we are using only ACSR conductors. Then coming to the line supports. Once again, before choosing the line supports, we have to see what are the various properties. Based on that, we have to choose it. The line supports are, it should have high mechanical strength, light in weight, cheap in cost, and economical to maintain, longer life, easy accessibility, because we have to erect the transmission line even in the hilly areas also. So transportation, if the weight of the entire the support is less, then it is easy to transmit and handle. So that is it. The earlier days we started with wooden poles, then that is replaced with steel poles. Nowadays we are using RCC poles up to 33 kV distribution, primary distribution, and after that we are using steel poles. Yeah, wooden poles. Even though we are not using, just to know about how the historical development of pole structures, the wooden pole, they are made up of seasonal woods and are suitable for lines of moderate cross-section area. The main problem of these wooden pole is you have to regularly maintain that. That is the main area, main drawback of this. Comparatively, lifetime is smaller, cannot be used more than 20 kV, less mechanical strength. Then we went for steel poles. Steel poles are often used as substitute for a wooden pole. They possess greater mechanical strength, longer life, and permit longer span to be used. Such poles are generally used for distribution purposes. Here also corrosion problem will be there in steel poles. So that is why we go for RCC poles, reinforced cement concrete poles. This reinforced concrete poles have become very popular as line conductor basically. Wherever you are going across the road, definitely you can come across these RCC poles. So that's why I'm saying starting from 230 volt single phase distribution, 415 volt 3-phase distribution, 11 kV primary, 33 kV primary distribution. Up to that we are using this RCC pole. Beyond 33 kV, starting from 66 kV, 110, then 400 kV, 765, 1200, everywhere we have to go for steel tower. Accordingly, the height of the tower will be more. Yeah, these are some of the diagrams. You can see that steel towers where there are these are all called suspension insulators. That we didn't touch about the insulators. These are the various insulators which are used in the line. The first diagram is 110 kV span, 320 meter for single circuit. Second one is for 220 kV span, same span of 320 meter, but there are double circuit. You can see that there are 6 conductors present. Then, how to reduce or how to optimally choose the size of the conductor? That's the next point. The economic choice of conductor is based on Kelvin's law. What Kelvin's law state is, see, whenever your annual charge on the capital outlay and annual cost of energy wasted is meeting at a particular point, that is the operating point where the cross section of the conductor you have to choose. So that is a statement given by Kelvin's law. There are some physical, many drawbacks are there in this Kelvin's law in the practical implementation also. Depreciation, the decrease in the value of the power plant, equipment and buildings of the everything is called depreciation. Due to depreciation, even if you are designing a plant for 1 ton, for example, there is a plant which is generating 200 megawatt of power. It may be a 10 years old plant. If you go and measure the maximum generation capacity of that, it may generate only 180 or 190 megawatt because of these depreciation. So aging is factors of this. So the annual charge, how to find these two? To find the annual charge, there is P1 plus P2A. Using this expression, you have to find what is the annual charge, where P1 and P2 are the constant and A is the area of cross section of the conductor. Annual cost on energy wastage, that is P3 by A, because area of cross section is inversely proportional to resistance, because the resistance, based on the resistance only the annual cost is varying. That is why. Yes, if you find the total annual cost, if you add these two costs, we are getting P1 plus P2A plus P3A by A. To find the effective cross section, differentiate this with respect to the area by A, and you are getting a condition that P2A equal to P3 by A. According to Kelvin's law of statement, whenever that variable part of the annual charge is equal to annual cost of the energy wasted, at that point, whatever the area of cross section you are getting, that is the effective area. But sometime if you choose that area and if you go and see the current capacity of that, maybe you are not meeting the requirement. So that is a main drawback of Kelvin's law. Once again, the numericals based on the Kelvin's law.